Thank you, everybody, and thanks, Burkhard, for the extra time. I'm gonna try to be as quick as possible and jump to the classic noise factor I was started yesterday. And yeah, sorry again, I was not quick enough to explain everything, but we have a lot to unpack, and maybe this gives me time to go a little more in the detail. As you can see here, is kind of representing again what I was showing yesterday. The first test is our reference with the absolute values and then the delta respect to that test. And we investigated several different things. The surface mesh using the new AutoCFD4 mesh. As I was saying yesterday, we use this case using the original plaint, so not without the groove open. We want to decouple, let's say, the surface mesh on the vehicle respect to the opening of the groove. And you can see from the line below, the groove plaint actually on the tires, they're actually having a much bigger impact on the results in terms of drag changes, and especially in terms of front lift changes. Interestingly enough, with PowerFLOW, we can remove completely the plaint because we don't have, let's say, this other solver problem of mesh that collide on cusp or, let's say, two facing elements one to each other. So we can also run completely without the plaint, and we can see that the effect is basically the same. So really what is matter is those groove channel open around the tire. The other things we tested was simulating the engine bay of the vehicle, so opening the holes on the wheel arches and at the back of the vehicle and reintroducing the volume there. So it's adding fluid domain inside the engine bay with a representation of the engine bay that's supposed to be correct. This has quite a big impact on drag and still, again, a quite big impact on lift values. I would say we get closer to the experiment with the rear lift, but we stray much more with the front lift. And this, again, it's kind of something that we have to assess, but the drag values with that change would get closer to the experiment. Other small changes that we did, actually, those ones were more intended to, so those are kind of big changes we did on the geometry, and we know that they will bring changes in terms of factor that were significant. Smaller changes that we tried to see the impact, which can fall more into the noise factor ideas, let's say, is removing the glass from the mirror, so just removing on a separated surface, something that it should be considered minimal. And we can see that the results here is minimal. I should have mentioned before, these are all results that are with our simulation run monitor considered accurate within 1 count accuracy for the drag value with a 90% confidence level. It's written very small here at the bottom, if you can see. So the delta that we are seeing is well below that soil, so we can say that this is kind of below the threshold of the uncertainty we have, so it's a very small noise factor if there is anything. Same goes removing the ribs on the transmission of the engine, which again was another detail that was considered how should influence the flow field. It should be a very small impact. And we can see again that for drag is a very small impact, is maybe bigger for lift, but again, the accuracy of lift might be affected by the simulation time that is based only on drag accuracy, not on lift as well. Worth to mention as well the domain size. As I was saying yesterday, we use our standard best practice and our standard template, which size the domain of the vehicle respect to the size of the vehicle. So we were not one-to-one respect to the prescription, let's say, of the standard case, the AutoCFD case, as suggested. So we scaled our domain to fit exactly the same domain. And again, this does very minor change. Again, I will deem all of them falling inside the accuracy level. Drag is definitely within that. And for the lift values, we are scattering around 1 count, 1.5 count, which is probably, again, a wider spread that we have on that accuracy. The last two are grid resolution change. So our reference is what I was calling yesterday fine grid change, which is the standard best practice we recommend. And as we mentioned yesterday, PowerFLOW, let's say, time steps and grid are coupled together. So as we scale the size of the grid, we will also scale the time steps. So for the fine resolution, which is most of these results, we have about 6 microseconds in terms of time step. We mentioned that yesterday as well, that Lattice Boltzmann time steps are very small. So we are 3 orders of magnitude higher than the ES methods. But both the medium grid and the coarse grid are sharing scaling up on that time step. We go from 6 to 9 microseconds. And the difference is that the medium grid has additional resolution locally to compensate for the global coarsening of the mesh, while the coarse grid is a global coarsening of the mesh. And you see that the medium grid is actually capable to balance the effect. So we can coarsen generally the domain, and re-adding resolution locally, we can kind of keep things balanced. And obviously this brings a certain performance benefit. The coarse grid, on the other hand, is something a little suspicious. We have to investigate our end as well. It's a bit bigger than what we would expect in terms of delta, but definitely we recorded a shift in drag that is way too significant. It's a big noise factor that would not be considered acceptable, let's say, for general development. Definitely a step that we have to do there. More in depth is looking more in depth at the effect of the front wheel deflector, for example, to understand if it's just a shift, but the main, let's say, the main flow feature are still well represented, and we can get the good results. Very quickly, maybe on some, I don't know, I have a few minutes, maybe still. 1, 2 minutes, okay, perfect. This is the effect of the AutoCFD4 mesh, so the finer mesh. And as I was saying, the effect is pretty small, and you can see here on the pressure results on the surface, there are very small effects on the upper body. There are quite clearer effects maybe at the front, which is probably where actually a higher resolution is beneficial for having a good definement, let's say, of the radius of the bottom part. And there are some bigger effect here around the side that is probably due to a finer resolution on the tires. So generally speaking, it's not a big effect. There are some local area. That's PowerFLOW. It's kind of fairly independent from the mesh of the surface mesh that you are giving, as long as you represent well your geometry. So as long as the detail are well represented, and as we can see here, there are just very local changes. On the other hand, if you oversize your mesh, you can have a performance deficit, which is in this case can be up to 50% of simulation cost. Other stuff for the front wheel deflector. Sorry, from the groove, it's quite clear actually the effect is concentrated at the front, and we can see that this has a big effect on the front part of the vehicle, as we would expect. So it's kind of capturing correctly what we would expect opening those grooves. And for the grid, this is the medium grid. Again, there are factored, let's say, changes here and there, more or less balancing out each other. So at the end of the day, you end up with the same drag values, but you can see that from the drag development, there are shifts that are running around. And I will not take more time from the kindness of Ulrika, so thank you very much.
Okay.
Thank you.